Yeah, another draft physics video presentation. Such. Yeah, to slit it some more and interferometer stuff and try to just illustrate the rather simple, kind of obvious oversight of physics, a little bit of lack of detail, a little bit of lack of curiosity, lack of will to make sure, kind of thing. So jump to the conclusion. Don't bother, looking at what you're jumping to. So anyway, and this is just another video. The same jargon, the same story. Just you know, whatever the preachers say. And they're making kind of an argument in a sense, and this is sort of a presentation, a brief of like, this is our evidence, and this is why we believe it, but the evidence is really bad, and it's, presented in such a poor context that, they're kind of hiding the real truth. They say, well, we got hundreds of witnesses, and they only have one witness. And, it can't be denied, and the one witness was drunk, it just doesn't take much. Like I said, I've sort of used you don't have to scratch on the veneer very hard to find out it's all plastic and crap and shit. It's just paint. It's not, this isn't the real deal. Their evidence is horrible, and it's way past time they admit it. I mean, they should have found it out themselves just by shaking the thing, just by working with it. They should have noticed how flawed this theory was, but they haven't. And it's a pretty horrible example of just intelligence gone way wrong. Not even obeying its own principles, repeating experiments and being careful and all that kind of stuff, and they just didn't do any of that. And just really bad science.
If you've read Brian Greene's The Elegant Universe, one of the first lines is that to understand...
Yeah, it's one of the last things on Earth I would find myself doing, probably. Brian Greene. Can't jump up and down, I guess that's the good news. You can't be jumping up and down in a book. What am I looking for? Sound. Where the hell's the sound? I knew something was missing here. And all the properties are missing. I can't. What the fuck? Oh, it's way over here. Okay, sorry. Yeah, there. That should be enough. Sorry. Could have paused, but I just didn't think to do it in time.
Understand the quantum world, you need to forget everything that you think you know. I love this line because it really...
It's just a horrible line. It's just, you really don't. You shouldn't have to do any of that. The truth, the small universe can't be more mysterious than our world. It doesn't make any logical sense that it has properties that our world can't exploit. If particles could be entangled, then cockroaches would be entangled. If there was something for them to take advantage of, if there's something for nature to make as a tool, it would have made a tool out of it. And the biological organisms would have all of these features of being superimposed.
Hammers home the message of just how weird quantum mechanics is.
How undeveloped it is, unfinished, unrigorous, sloppy. There, that's the word. It's really sloppy logic.
For example, if I were to throw a rock at your head, at no point would you expect it to diffract around you like a wave in a lake.
But I'd have every expectation if you threw tennis balls at me that some of them would bounce off of me in all kinds of directions, that some of them would barely hit me, and some would hit me square on and all that kind of stuff. And that would be the more appropriate analogy. It's not even close to even trying to get to the truth. And it's so obvious in these slit experiments that the surfaces are the first suspect. It's like the husband, when the wife is found in a, pool of blood. The first suspect is the husband. Come on. First suspect. And in this case, the first suspect has to be, well, what are the surfaces doing? What are they made of? What do they look like? From a photon's perspective. That would be the logic. And as soon as you do that, you realize, oh, this is a lot different than throwing a rock at somebody.
You'd simply expect it to hurt. But on the smallest scales, the rules of what's a solid piece of matter and what's a wave blur.
Well, see, that's the funny thing. What's a solid piece of matter? And you don't pay any attention to those, that fact. That the idea of the surface being some sort of all or nothing thing doesn't really make sense on an atomic level. That you can understand atomically, that's not really what it is. It's got to be made out of atoms, and the atoms have this weird, more positive in the center, negative on the outside. They have a real form to them. So if I'm going to make a surface, I'm going to know it's going to have more electrons on it than protons on it for sure.
Together in what's known as the wave-particle duality.
Which is known as the silly, somehow, we're not going to take responsibility for the evidence and actually make it coherent. So we're going to say the guilt, non-guilty, guiltiness. It just doesn't make any sense. The innocent guiltiness. It has a high innocent guiltiness.
When science was still young and new, it was assumed that the smallest units of matter...
It wasn't that new. We've been doing this for 10,000 years. Some things are pretty obvious. They don't change. Round wheel, makes sense. Square wheel, not so good. So we're learning and still, picking at it. And the point is in the early 1900s, you all decide to get really confident and really bold and make all kinds of assertions, even though your past record was really bad, that you made a lot of bad guesses. You couldn't even assign plus and minus right. Kind of obvious thing. They got like up and down wrong. They had to, and they never fixed it. They just decided to turn the whole world upside down to make it work.
Were all particles. In many cases, things could be modeled this way, and it made the math really straightforward.
Right, so he's pro-particle. Yep, okay, it's pretty obvious that, most of this stuff acts as if there's real stuff moving in real directions at real speeds, and you can, in fact, draw straight lines and make it all make sense. But we have some reason that we're not going to do that, because we don't like it. I don't know, what's their reasoning? Oh, there isn't really any.
Point-like particles can be modeled, as could their motion and the effects of their motion. But it didn't take long for scientists to find holes in that line of thinking.
No. It didn't take them long to try to jump at any bit of evidence that gives them some hope of the reverse. And that's what it seems to be, is that they really didn't want to give up on something fantastic. Something life-endorsing and universe-endorsing. They didn't want to see it as, it really is a bug universe. We're on a bug planet in a bug universe. It just makes robots. Stupid ones. Mostly.
One of the first demonstrations of the wave-like nature of the quantum world was the famous double slit experiment.
Right, which really shouldn't be famous because Newton had already done the two experiments. He had done the what happens when the surfaces are facing each other experiment, and he did the what happens if the surfaces are facing out experiment. So he's basically done the two experiments, the only experiments that mattered, because it really was about surfaces. And so then all the young double slit does is, it just gives you these two things, where you have two outside surfaces and two inside surfaces, really. But it's really just surfaces again. And Young did it so badly, he didn't even realize there was a much more complex pattern to be revealed. And his math doesn't even add up, which is even funnier. That as bad as it is, he should have been able to figure out that wave centers in the center of the openings, that math doesn't get the right answer. So it was bad in a lot of respects. I mean, they had 100 years from 1801 to 1920, over 100 years to figure out that, hey, wave math doesn't even work. So why are we bothering with that theory?
The experiment is pretty straightforward. All we have to do is shine a light through a pair of small slits and project...
And this is the other part is that, like I said, Newton had already done the small aperture experiment, and shown that the same phenomenon takes place with just a single slit. So the experiment that's more anti-intuitive is the single slit. That's the one that really, whoa, what the hell? Where did all that crap come from? But if you understand it, that's really the single slit is really the two surface experiment, and the double slit is just the four surface experiment.
Project the result onto a screen. Before we see what happens with light, let's look at what happens if we scale this up and use a baseball instead of light.
Right, now this would be a perfectly reasonable thing to do, but they don't analogize at all like waves. They don't give the baseball the fair properties that they give their own waves, which is their waves come as a bunch of waves. They have time. There's lots of them, and the period is basically the, from peak to peak. So they give the wave properties, and they won't give the particles the same properties, and that's where this all. I mean, that's the first glaring, like, well, you're not fair. You're not making a fair comparison. Why are you prejudicing, the obvious? Why are you taking the obvious away from what if you want to analogize, you have to add the, you have to do a proper comparison, between things that are comparable. Okay, this is where I should pause. All right, eyes back. Okay, so we're just going to do this simple thing. It's a fair thing to be doing. I mean, we could just do one slit, but it doesn't matter. But let's say we were going to throw baseballs at it. You could understand that, okay, well, how do I analogize a baseball to a wave? I mean, how do I make a fair comparison? I mean, I'm going to draw waves, and I'm not going to draw just one of those, right? So why am I drawing one baseball? And if I know the wave is defined, I mean, its frequency is defined by this separation, the high and then the low and then the high and then the low. Well, wouldn't the fair analogy be that I would have baseball, then baseball, then baseball, and there would be like a little timed interval here of like 500 seconds or, milliseconds or nanoseconds or whatever you want to call them. Something commensurate to a wavelength. So this would be the fair comparison, wouldn't it? That I have a stream of baseballs, and that I could have more than one stream of baseballs, just like this wave spreads across the whole area. Well, I could shoot baseballs all day long, right? I could fire from 4 different baseball throwing machines or 10 different baseball throwing machines. So I could have lots of baseballs going towards these slits, right? I mean, that would be the fair way to do it, and that's not the way they did it. That's not the way they're doing it.
When we fire the baseball at the screen, if the trajectory lines up with the slits, it goes right through, but if it doesn't, the baseball is blocked.
So we know that this is horribly flawed also, because we know that I'm going to make this slit not just one baseball can get through, right? So I'm not doing that to the light, so why would I make it like that? And we know that the baseballs could interfere here. The baseball could just barely glance off the side of this and go that way, and that some baseballs go all kinds of different directions. Now, unlike light, we know the baseball is not likely to do this. That takes a certain special kind of hitting, and it's certainly not going to travel the same speed. But it wouldn't take much imagination to say, okay, I could understand that there could be, 10% of the baseballs that actually do scatter off the surface, in what would look like a wave. You could draw it like a wave, like the scatter would be, even, and that, and again, as long as you understand that you can't change the speed of the baseball, that's being fair. And of course, baseballs could draw exactly, the mathematical circumstance you need, the 4 waves with 4 groups of scatter. It creates exactly what mathematically works in terms of getting things to this other side. And all you're really doing is trying to reconstruct this phase. And the same thing happens with their waves, right? Their waves are basically saying, look, I'm going to combine pieces of wave. And so I'm going to take a piece of wave from over here, and I'm going to combine it with a piece of wave over here. So this one goes first. And then this one, because it went longer distance, this one shows up second. And then I get another component shows up third. And I'm just reconstructing a frequency. So that's all that you're really doing, and obviously a baseball can do that. If I send a frequency, I can ruin it, that is, have baseballs flying all over the place, and there would be places, though, that mathematically the lines will add up. A baseball from here will hit first, and then a baseball from way over here will hit second, and I'll reconstruct a frequency. So it's, a fair comparison. Doesn't leave any gaps, doesn't make this oh, what's so strange, particles can't do it. It's impossible for a particle theory to explain it. Well, no, it isn't. If you make the particles exactly what you make the waves, which are, well, the photon's a composite. The photon isn't just one of these things. It's not one line. They know that. They know they can't make a photon with that. I can't send a radio signal with that. I can't just send, well, there, I sent that. That's not, you can't tune it in. What's that? It's not a signal. The signal is a pattern. And all you're doing is taking a pattern, you shove a pattern into this obstacle, and it's clearly obvious to be an obstacle. So you send a pattern through an obstacle. The obstacle breaks the pattern. Pattern's a little screwed up when it's going out here. But the pattern can be reconstructed here out of different components of pattern that you broke. There. Answer. Solved. Not complicated. No duality needed. No waves needed, because we know the photon lands as in one tiny location, and waves just wouldn't do that.
If we record the point of impact and repeat this a bunch of times, we end up with two areas on the screen where the ball is hitting.
And so again, the flaw here is that then they'll use this as some sort of excuse to say, oh, look at the way the light that was here is now going someplace else. Well, that's not what happens. So, and somehow light plus light equals dark, which also doesn't happen. So it always has to be remembered that the slits in the light example are 1 millimeter apart, and when the lines get to the surface over here, they're still going to be just 1 millimeter apart, because you didn't let them bounce off of anything, right? So it's only a tiny percentage of the light that does this other stuff where it goes further away. And clearly we know it does do that. The single slit is glaring example that if I make the slit smaller and smaller, the pattern shoots out wider and wider. So this analogy that it does this little straight line thing, there's no reason for particles to do that either. The smaller I make the slit, the more likely the baseball is going to hit it. Duh.
For particles, this makes sense. There's no reason to think that we should expect anything else. Now, let's do the same thing, but instead...
No, I think I forgot to switch to the drawing board when I drew all that stuff, huh? Well, work in progress, sorry.
Instead of baseballs, let's do this with waves of water.
I could just re-emphasize it, but there's no point. Okay, so this is just off the Wikipedia page. So again, this math won't work. So they just keep showing it. Like the center of the wave can be the center of the slit. That's not in the math that works. The math that works, the surfaces are the distance. So it's not the center of the wave. So again, they just keep showing this as if this is accurate, and it doesn't work. It won't give you the right answer.
As the wave propagates and reaches the slits, two mini waves are produced on the other side. These then interact as they continue their journey to the...
So they say these things, oh, they interact and they do this and they continue their journey, and then but they won't explain that the real double slit creates two patterns. They don't even have that part nailed down. They don't explain why the little blobs of light don't get gradually light and then gradually dark. That's what they should do if they were waves. They don't explain why the bright spots are much bigger than the dark spots. They don't explain why there's two patterns, not one pattern. So, I mean, key features that are just glaringly in the pattern, they just pretend, oh, who sees that? We don't have to pay attention to that, do we? That detail isn't important, is it? It's not an important detail, right? I mean, yeah, all the details are important.
Screen. In some areas, they interfere constructively and get...
So then this citation to Veritasium, again, and this clip is in a video that's just a piece of garbage. In the sense that it's showing the young example, and it's such a bad example. Because the math doesn't work.
Stronger and larger. In others, they interfere destructively and get smaller and weaker. When these interfering waves strike the screen, instead of two spots like what we got with the baseballs, we get a very distinct...
So again, look at, they have the D marked as the outside surfaces, which isn't even right either. You know, it's the interior surfaces are the variable they put in the math. They don't pay attention to these outside surfaces in most cases. And obviously the double pattern they're not showing at all here. And the double pattern means that the center bar will be bigger. So they actually have, these two graphics aren't even consistent with each other, right? Because they do have the bigger central maxima in the picture, but they don't have it bigger spatially, you know, width-wise in this image.
Pattern of lines called an interference pattern. Okay, now we know what happens if we use particles and waves. Let's see what happens if we use light.
So again, it's just, you know, you didn't show us what happens to a pattern of particles, and you always have to say a pattern in terms of waves. It's a pattern of signal, on, off, up, down, whatever you want to say. It's a signal, a pattern. Pattern goes in, pattern is changed, and that's all that happens.
To really make this clear, I won't be using an animation. Instead, let's actually perform the experiment.
Alright, so this will be a waste of time. He's really actually not going to use this professional one for whatever dopey reason. Same one in the other video. You do have to wonder whether this is just a single slit, this one on the end. Frankly, I don't think it's a double slit, so... But anyway.
That we're going to need a double slit. If you live in the States, you can just buy a pre-made set on Amazon, but let's pretend for a second that we're the shorter the wavelength, the...
So we'll just play with this. So, yeah, I mean, it's just no point in going through the mechanics of making a crude one out of soot. But anyway, so now he's talking about the fact that the different colors of light have a different frequency, and that means they make bars that are smaller, more compact. And so the patterns aren't exactly, the bars won't be in the same location, quite obviously.
Smaller the angle of diffraction. In fact, you can actually use the double slit in place of the diffraction grading that we used in that video, and the math only changes slightly.
Well, again, he's still showing this example that's just wrong. He's just not consistent with the math that's actually used. So, you know, comparing angle lines from the center of the impediment doesn't even make any sense logically at all. Just attempting to do some averaging, which isn't the real experiment.
The result was first published, people briefly thought that this was the end of the discussion. Light is simply a wave. But that didn't last long. Thanks to Louis de Broglie, we
So this is the real silly part. Thanks to, they always have to say some sort of crap like that. And this is all just really bad physics in the sense of giving, you know, assuming that frequency is momentum when it really isn't. Frequency is just very handy when you want to add energy to a system. You pay attention to frequency, resonance. That's all it is. So it's frequency only has meaning depending on the system you're interacting with. But it isn't in and of itself energy. It's not really extra momentum. It's just not.
Now know that all particles have a wavelength and behave both as a wave and as a particle.
Yeah, we don't know that. So I mean, you know, people just won't say, "Oh yeah, okay, I admit that's way too arrogant." I can't get one critic to sit there and just type that and say, "Yeah, that's just so obnoxious that they say that kind of stuff," because they really haven't proven any of that. They haven't proven that an electron has some sort of innate frequency built into it somewhere. That somehow it's running around going, I am 600 trillihertz. Come on. That has some label, and that has some, like a pancreas or something, and the pancreas says, you know, 14 trillihertz. No. It doesn't have any feature that makes it a wave. None. Zero.
This is known as the de Broglie wavelength. The way that this was proven was by repeating the
It really wasn't proven, so, you know, so again, and so they just won't admit that they really shouldn't say proven, because they're not even describing the actual experiment. I mean, they're making the experiment up in their head. It's a thought experiment that they've pretended they actually did, and they never did it.
experiment with electrons instead of
Okay, so they never did. There's no double slit experiment with electrons. I mean, the only one that comes even close was one done inside of an electron microscope. And it's still, you can just point out all of the glaring errors in the logic. Again, the surface, any surface is going to be charged. How could you possibly say I'm doing the same experiment when you know the electrons are charged and you're going to force them through a gap that's charged? There's no such thing as uncharged, frankly. There just isn't. Okay, there's atoms always have electrons in their surface. And so the electron is obviously going to be more likely to interact with another electron. And that's going to be a charged interaction. It's not going to be some free interaction.
photons. We already knew that electrons were definitely particles, and yet when the experiment was repeated, a diffraction pattern.
So again, it wasn't repeated. It's not the double slit experiment. This image is from scatter off of a surface. These are electrons fired at a surface, okay, at an angle, and reflected off the surface of a crystal. It's not the same experiment. And you'd have good reason to understand why surfaces are, overtly. So here I've been arguing that this experiment is really about surfaces. And they're sort of proving it by doing an electron experiment where you're overtly crashing the photons into a surface. It's clearly not some kind of Heisenberg gap problem. It's not some sort of, this isn't, you're confining the electron and it doesn't, you might find out too much information, so it's going to wiggle away to make it uncertain where it is. And I mean, none of that makes any sense in this circumstance. You're overtly shooting the electron at a surface, and then you're surprised that there's rules about how the electron is reflected. There should be no surprise. There currently are rules about reflections. The sunlight shoots down on us, and glare is made out of in the places where the sunlight reflects so purely that it retains, it's only got one polarization. Okay, only one polarization of light. That's why polarized glasses take away the glares, because all of it is in one alignment. So it's sort of like it had to be going this way, coming at the surface. If it was polarized this way, it doesn't create glare. If it polarized that way, it doesn't create glare. This way, yeah, it can create glare. I mean, there's already rules that tell us, they are a clear indication that banging shit into a surface doesn't mean it just randomly scatters. Because it doesn't.
Still showed up. This has now been repeated with larger and larger particles.
So again, more talk about experiments that we have no evidence about how they were conducted and what kind of circumstances and all that. I mean, the bigger the object, the higher its frequency, which means the slits have to be smaller and smaller, which doesn't make any sense, right? So if I have a buckyball that has a 1 gazillion trillihertz frequency, I can't make a slit small enough because I would have to be smaller than an atom. So how can I make a slit to push that through? That would be proportional and allow for the wavelengths of difference to create the pattern, right? I mean, these are wavelength differences. These are lines, vectors, that create the pattern. Well, in buckyballs, there's no way to do it. There's no way to have the same scenario. There's no way for the waves, if it was creating waves, to have any possibility of interfering with each other and create a pattern we could see. It'd be impossible for us to see the pattern. So obviously, if they do the experiment and the buckyballs create a pattern, it must be created by some other phenomenon, frankly. Because the interference one doesn't work. It has no mathematical hope.
All the way up to C80, which is a cousin of the buckyball made up.
So again, it's and go ahead, tell me what its frequency is. See, they think mass is frequency. So because of that, buckyball has so many atoms in it, it has a gigantic frequency. I mean, it's just, the wavelength is tiny, tiny, tiny. And obviously a slit the size of an atom would provide hundreds of bars, hundreds of thousands or millions of bars So how could you possibly see millions of bars? That would be impossible.
Of 80 carbon atoms. There are even some groups attempting to do this with entire virus particles. This is what is meant by the wave particle duality.
And what it should be is this is what is meant by silly, stupid, crazy physics. I mean, it's just so loop-de-doo nutty. You might as well be, fringe science. Because you're just so desperate to validate a silly story. And it's a silly story. We already know it's silly. Okay, all of us already know that basketballs going through hoops and stuff aren't interfering with themselves.
Even things that are definitely particles can still act like waves. There is a cutoff size, though.
So this more de Broglie bullshit. Now, we have an imaginary cutoff size. No, your cutoff is as soon as you get into the quadrillion hertz, you're already done. Okay, as soon as your frequency is smaller than the width of an atom, you're all done playing this silly interference game.
The larger a thing is, or rather, the larger something's momentum, the smaller its wavelength.
Right, which makes none of this whole conversation nonsensical. Because again, the buckyball, I can't tell you how high the frequency is. It's an insanely small wavelength. Just insanely small. A billion times smaller wavelength than an X-ray. How do you build slits for something that has a wavelength that tiny? How do you confine, in other words? The only way you can see the pattern is the number of bars it creates has to be low enough to make big enough bars. So if it makes a bazillion bars, you do understand that a bazillion bars over any 180 degrees, it doesn't matter how big I make the 180 degrees, I would have to display the pattern on Alpha Centauri, in some place in space so far away to have any hope of seeing the pattern because the bars are so frickin' small.
This is why things like a baseball don't behave like a wave. They have too much mass and momentum to show any sort of difference.
A buckyball has too much mass and momentum. Again, it has too much frequency. An electron has too much frequency. Again, it's more than X-rays. It's more than gamma rays. It's an insanely small frequency. You can't build a slit small enough to do the experiment. It's theoretically impossible by their own mathematics.
Diffraction pattern. But it gets stranger. If we slow things down and shoot individual electrons or photons, a diffraction pattern slowly builds over time. This implies that the particles are somehow interfering with...
Yes, well, it implies, but it seems like, looks like, this isn't very good physics. So clearly it does show you that the pattern is made compositely. It's made up over time. So that should be some clue it's giving you. But the fact is that this whole idea that you know what a single photon at a time is, like I said, the original French experiment happened over a month or more, right? The story is the French guy puts the photographic paper up, creates a black screen that has a couple of flaws in it somewhere, like the hope of a flaw. It's just enough black where some photons eventually get through, occasionally. And then he goes off sailing for a month. So that's the original experiment. I mean, allowing the photons to be so unfrequent that it takes a month to expose the photographic film. They haven't done that experiment. They haven't repeated that one. So all of these single photon experiments are all happening within seconds or minutes. And, you could argue that, well, you really don't have a guarantee that these are single photons then.
Themselves. The only way this is possible is if the subatomic things have both properties of a particle.
Right. So we have to assume first that your experiment has actually been conducted properly, which it hasn't. So Veritasium attempted it, and clearly the video shows that the only way you can get it to work is to way up the amplification on the photodetector. So he had to create 7 error photons a second. And that forced him to do the experiment in a shorter period of time. And doing the experiment in a shorter period of time means, the fact is there are more than one photon going into the experiment at the same time. That's just a fact. You guaranteed it in a sense. By speeding up the experiment, you basically guaranteed that, yeah, every now and then you get two photons in there at the same time.
And a wave. But this also implies that the particle is going through both slits at the same time, which doesn't really make sense.
Right. So you should stop at the parts that don't make any sense, and you should think about them. Start thinking about what a surface is, and the fact is that the pattern is what's getting broken, and that you're just recapturing a pattern on the other side, and it's not made out of the same stuff. It's just that it's all parts. There's something made out of parts, A, B, and C, and you can have different arrangements of A, B, and C. And all you're really saying is I sent in a bunch of people that were A, B, and C, and the fact is yeah, they broke. So their heads popped off, their torsos went one way, and their legs went another way. And all I'm doing on the other side is just putting back together again head, torso, legs. It doesn't have to be from the same people. It's just the right order. And that's all you need, is the right phase.
Take a second to let that sink in and appreciate just how weird that is.
Yeah, well, to appreciate why this physics didn't do any real inspection to say, well, is it true first? Let's first establish that this is really true. Yes, it's weird if it's true. Is it true? And that's what they haven't done.
And worse still, if you try
and yes, and worse still is they keep going further and further in terms of, oh, and then we put detectors, and then we did this, and no, you never did any of that stuff.
Measure which slit.
See, there, you threw the eyeballs on it. I didn't even realize that was in here. Look at that. I mean, this silly notion. I put the detector on here. You can't detect photons passively. It's impossible. If the photon goes to the eye, it didn't go in the experiment. Okay, so the detector can't work. Isn't possible. Electrons, you also can't inspect electrons without making a mess out of them. There's just no way to reflect anything off of them. It's like you seeing a car by throwing bowling balls at it, okay, or cannonballs. You're not going to see the car where it is. You're not going to see it in any kind of reasonable condition. You didn't passively observe it, reflecting cannonballs off of it. Come on. It's a silly idea. It's theoretical nonsense. They cannot be inspected. They can only be overtly, catastrophically changed. Interactions between force and matter are, in a sense, complete. You either interact or you don't interact. There's no, I interacted so little that I didn't even affect it. There's no such thing. You either knock their heads, torsos, and feet off, or you don't. So you either don't interact, or you really do break them into pieces, and you just reconstruct pieces. And that's all you can ever do, is reconstruct the pieces.
It collapses the wave function, and things start behaving like simple particles.
So he's telling a story that's completely unevidenced. Absolutely zero evidence. There's no historical record of any such experiment detecting any such things. It's impossible theoretically. Every scientist should know. I understand enough about this physics to know there's nothing I can shoot at an electron. Electrons are catastrophically affected by photons. If you want to move an electron, you shoot photons at it. Magnetism. You shoot something, whether they call it a virtual photon or a real photon. The point is that's what you shoot at an electron if you want to move one. How the hell can I use that to detect one if that's the thing that makes them move? Right, you can't.
And the pattern disappears.
So they say the pattern disappears, and just like I said, just doing common sense, you could say, no, the pattern should get even more bizarre, right? I mean, if I'm actually disturbing the electrons, that is to see one, I'm, banging the hell out of them, changing their direction, then I should see even more pattern, because now I've essentially created another surface. I've created another influence that's going to beat the hell out of the electrons. So it shouldn't be that the pattern goes back to normal. So this, like I said, this experiment was never done. It's just a fable. This is just complete nonsense. And you're saying, here we are, 2020, and we still have people believing in Jesus stories, of walking on water and raising the dead and all of these preposterous, Moses parting the Red Sea. And even though all these people, humans at the time, were supposed to be witnesses to these miracles, none of them were very convinced because, a few years later, they're all wanting to go back to Pharaoh in Moses' case. They're starting to make gold bulls again and pray to fish gods and shit. So I guess they weren't too fucking impressed by this whole parting of the Red Sea. So we know these are stories. And so here they have a story to try to force this evidence to mean something. I'm going to tell you a story. And that's all it is. It's a story, not a shred of evidence to defend it. Nothing. There's no theoretical ability to see passively, to passively observe either either electrons or especially photons. It's just impossible to see a force. It's just impossible.
Because to measure or observe which slit something like an electron is going through requires bouncing another particle like a photon off of it.
Well, there you go. So why don't you just admit it's impossible then? Because there's no evidence you can bang a force off a force. And there's certainly no evidence you can bang anything off of an electron, anything smaller than a photon. That's all we got is photons to work with, and we know photons move electrons. So you're done right there. They move them a lot.
This fundamentally changes the nature of the interaction and destroys the effect.
Well, they said it destroys the effect, right, again, but that's just they have already written, they wrote the fake story and they wrote a fake conclusion to it that, the pattern went back to normal. When, again, all I'm saying is you can just intuitively know that, no, if I'm creating more agitation to the electron, I'm going to get more pattern, not less pattern.
Not everyone agrees why this happens.
Yes, you all do agree. That's a lie, too. So, again, where do I find the person disagreeing? Where do I find one establishment character who disagrees? Beyond Einstein, where do I find that person? So that's a silly story. A silly can say, "Oh, well, not everybody agrees." Well, where do I go to vote for the other guy? Where do I go to support him? I'll give him some money, because where is he? Where's the scientist fighting for the rational theory? Because I can't find one.
To this day, physicists still fight about it.
So where do they do that? I haven't seen it anywhere. You can't even mention the subject on a forum anywhere. They just kick you the fuck off. You can't even suggest it without being ridiculed and killed. So this is just such a story he's telling. Where's this argument? Because it doesn't exist. All you're arguing about is Mohammed, Jesus, or Buddha or something. You're just arguing your silly who's wooier theories. Woo, double woo, or triple woo. But there's no unwoo out there.
I won't get into all the variations, but there are three main explanations.
So this just has to do, again, with interpretations that are all based on the premise that it's true, that this isn't particles, that this is some sort of magical crap. Magical random. The random God did it. That's Feynman's answer. Copenhagen answer is everything's entangled and superimposed and, wooey nonsense. And then you got people who think there's a new universe every gazillionth of a second. A new universe was just created. I can't even say gazillionth of a second because it's happening even faster than that. There's new universes happening. It's so fucking insanely silly.
That mathematically give the same answer, even though they're completely different.
So again, they don't mathematically even work. So let's just understand they get the wrong answer if they put the waves centers where they draw them. So if they put the waves where they draw the waves, you get the wrong answer. Fact. Just ignored by this guy and every other physicist.
These are the Copenhagen interpretation, the many worlds interpretation, and the pilot wave interpretation.
Right, the pilot wave interpretation has no hope of creating the complex patterns. Let's understand it's dead in the water because it's creating a single slit pattern. It's essentially. There's no envelope in their math at all. They can't account for the envelope pattern, let alone the non-existence of the gradual on and off, which it also predicts that doesn't exist. I mean, it's mathematical garbage. Doesn't predict the size of the center maxima. I mean, it's, I'm sorry, yeah, I'm pointing with my mouse, which I'm not allowed to do. Whoops, I can't do that either. Ooh, don't do that, Gary. I had this figured out ahead of time and I messed things up. But anyway, so this is the whatever you called it. Pilot wave, I think, theory. This is Copenhagen. This is the multiverse over here. But this doesn't work. You can see it just looking at it. It creates one pattern. It's like, the two-wave theory. And it just doesn't work. It won't create the complex pattern. And again, it doesn't account for what we actually see, which is, bars of light. They don't get gradually brighter and gradually darker, and they don't do any of the things this theory predicts. And it's that overt. I mean, it's that overtly insufficient as an explanation. It doesn't do the envelope, and it doesn't do the actual stuff won't be in the right place. I mean, the bars won't be the right size. Okay, back to the video.
Personally, I like the pilot wave interpretation the most, but we'll have to explore these in a future video.
Yes, well, I'll have to go find that because, again, liking this the most is probably a big mistake on your part because it's really lame.
As I think the only way to discuss them appropriately is to cover some other quantum experiments first and see why they lend credibility to one interpretation over the other.
And they don't. So again, they're just all underanalyzed. And the more complex the experiment, the more they slough over, the more they just jump over, slide over all of the details that don't work, that don't make any sense, and don't fit.
However, if you're interested, I've put some links to other great videos that explore each in the description. Okay, so now that we know that light behaves like a particle and a wave...
No, we don't know that. So again, there's such propaganda. Now that I've vaguely told you that it seems sort of like, and if you squint your eyes, you can see it that way. And if you really don't pay attention to the math and being explicit and being accurate, you can believe. That's the proper premise for this. You haven't made a good argument at all. The logic is horrible.
Can we actually make...
And the evidence, again, it has glaring pieces in it where you're just making it up. You're just reciting a biblical story. You don't have any facts here. You don't have any facts about any detector experiment.
Use of this, or is it just a fun science fact? Turns out...
Well, the whole industry of science is based on you emphasizing these wooey explanations and now creating frequencies and objects that don't have frequencies and all kinds of nonsense. You've broken your own math by again, this idiotic notion that momentum equals frequency. The two things are not the same thing. There's obviously correlations. Obviously, if I shoot bullets faster, more bullets are going to hit the target in a certain amount of time, and that's going to be more energy. But the bullets don't have any extra energy. The bullets are all the same. Bullets don't care whether I fire one today and then one 10 years from now, or I fire them a second apart. They don't care. They do their own thing. They're not in any way required to be more energetic because they're in a parade. No, they're the same. Whether they're on the parade or they're in the garage, they're the same thing. Continuing.
It's actually a really useful property. To make use of it, we're going to need to upgrade our setup and add a bunch of other components. Allow me to introduce you to a really cool device called an interferometer. We're going to be building...
Alright, so he's going to use Legos to make an interferometer. So we won't bother with, beyond... we'll do the drawing maybe. It's just the standard setup. And again, not accounting for any of the known properties of the mechanism. What a beam splitter requires. And the fact that the beam splitter can't really be understood to create two equal beams, because one beam has to travel a completely different obstacle than the other beam. So how could they be the same if they did something completely different? You know, I mean, one's going through a paint machine that sprays white, and the other one's going through a paint machine that sprays black. I mean, they can't come out of the process the same.
And a beam splitter to make the light interfere with itself.
So again, there's no interference. There's just, you know, changing the pattern. There's taking the pattern that's in phase. So two things come in and they're in phase with each other. They're lined up. And then you change the phase. Now they're not lined up anymore. Okay, they're off alignment. And that's all this is about, is fiddling with the path length of the bits of these quanta. So you're going to first scatter the bits, and then you're just going to sit there and say, okay, I have bits that are taking all kinds of different paths. That means they're delayed in when they're going to show up. And all I'm going to do is try in the end is collect the bits where the pattern lines up again, where it's the right distance between them. And that's all this experiment's about. Just about phase changing phase, creating noise, creating an unclear picture. And that's all it is. You just have a pattern going in, you screw the pattern up through an obstacle, and then you reconstruct pattern on the, in the end. You take the bodies and you break the pieces off like a Lego. Okay, the Lego head comes off, the Lego torso goes this way, the Lego feet go that way. And then you just collect. I got a head, I got a torso, and I got feet. It doesn't matter where they came from. You got them at the right time, it goes back into a complete photon. That's it. That's all that's happening in these experiments. All right, let's go to the one feature that's really important. Might as well just, I've already pointed this out, but this is the key feature of interferometers. And again, I haven't gotten anything close to a... All right, so on beam splitters, quick again. The idea is that the beam splitter is basically a bunch of holes, okay, in a substance. And he's using a cubed one, actually, which means that there's a film inside a cube, okay, a plastic film, a thin film. And the thin film has internal reflections, and that's what's actually going to create the spreading of the light. But the same principle that I'm going to describe is involved. So if the light reflects, light's coming in like this. We'll just make it a little bit thick so you can see it has a thickness to it. Light comes in like that, and it reflects. Well, then it stays parallel. Those are parallel lines. If it goes through the little holes, you can sort of understand that's like a single slit. And so it's going to come out spreading. Okay, just like the single slit experiment, little hole, big spread. So now this light's spreading. So this one reflects off a mirror, this one reflects off a mirror. Get rid of this because it's sort of in the way. And this is still going to be spreading when it's coming back. So just understand, it's still spreading. So it spreads the whole trip. The photons are moving further and further away from each other through the whole trip. This one, the photons are all staying in a group. And now the opposite's going to happen. Now this beam that was staying nice and narrow is going to go through the hole. Okay, and so it's going to start to spread. So it's going to spread a little bit. This one coming back this way is now going to reflect. And so all of its components are just going to reflect, but it's way big, okay, so because it's been spreading. So it's going to come back, it can't undo the spread. The reflection's not going to undo the spread, just like the reflection of the mirror can't undo the spread. So the spread's going to keep continuing because those are real angles. So it's still spreading. And so all you're really doing is just you're looking at the pattern created by overlapping these two patterns. So this one has a pattern of rings, and this one has a pattern of rings, a little pattern of rings. And you're just putting that pattern on top of that pattern, okay, in the sense of you can move these two so they're in the same place. And that's just parts. So it's really like the same experiment as the slit, in the sense that you're just saying, when I can align these two, there'll be places where they're more likely to be in phase. That is, even though the path lengths are way different. I mean, this one's spreaded a lot. These are older photons out here. This is a much older one, than the photon that would be in this position. Because this one to get here had to spread a lot more. I mean, had to take a lot longer path to get to this point. You know, if this was the point, the screen. So you're combining old photons with new photons, essentially, pieces. You know, a head that was broken off and floated around a little bit slower, you would think. I mean, you can use speed. I mean, obviously it never doesn't change speed, but you can use changing its speed to understand that the path length is different. If you have a longer path length, that's the same thing as moving slower. And so this is older pieces, and these are the new pieces. And you're just combining the pieces and saying, did I put a head and a torso and two legs together? And when I do that, then I got a photon. So this field is full of heads, legs, and torsos. You got heads, legs, and torsos. And as you combine these sources, you actually get 4 times as many. You know, the more sources you add, you square the number of possible recombinations. And that's all you're really doing. So where they line up, you got a 4 times better chance of making a human, you know, making a completed photon. One that's in the right phase, where the phase is restored. You're back to 500 nanometers. 500 nanometers distance between the clumps. So they're really measuring this. So it works as a measuring tool because with distance, this light spreads more. So it definitely measures distance, but it's not measuring a wavelength of difference. The pattern changes a lot slower than at a wavelength, a nanometer of distance. It's changing just on the spread, and the spread's a lot slower than the frequency, so to speak. The amount of change created by the spread is a lot less than the change created by a whole wavelength of shift in the frequency. The spread doesn't distort the frequency as quickly as just changing its phase. All right, probably enough. What am I trying to do here? Camera off. That's already on, and go. Yeah.
Before we get into the specifics of how this works, let's build one so that we can experiment with it.
All right, so he doesn't really get into the specifics. So anyways, this is just Lego showing you how I'm going to put an interferometer together with Lego. It's kind of silly.
So the end mirrors are carefully adjusted to make the beams overlap on the output. This is
Right. So, and as I pointed out, there's 2 things to understand that, you know, especially if you understand the cone's coming out of this, that if I tilt it a little, the cone's going to tilt. And I'm going to get very different alignments. Right? So any tilt in the mirror is critical when I'm sending a cone onto it. So when I'm displaying something that's not a single point, if I'm shooting a pattern at something, then the pattern can get, you know, all kinds of stuff can happen just by tilting it. So I can change things, that I can change the path length not only by making the path longer or shorter by moving the mirror. I can change it by tilting the mirror. Any tilt will also change where the patterns overlap.
This is done by carefully adjusting the mounting clips and moving the mirrors until all the dots overlap on the output. When everything is set up...
So overlapping dots just means he's taking these 2 patterns that are different sizes. Okay, and you can clearly see that in the previous video I played, where, you know, one of the patterns was gigantic, and just all you saw were the lines, and the other pattern was really small, but you saw the whole circle.
just right, an interference pattern shows up.
So the interference pattern it shows up whether you got it just right or not. The point is whether you get both patterns on top of each other.
It was really difficult to capture this with my camera, so I added one more mirror to reflect the output upwards so that it hits the ceiling. This makes the image much larger and the pattern easier to see. I wouldn't suggest adding this mirror until everything is lined up though, as it's harder to adjust things when looking at the larger image. The exact shape of the interference pattern is very sensitive to the alignment.
Yeah, well that's just which one's going to dominate, frankly. But you really have to understand that these straight lines are showing you a really big circle. They're really part of a circle that's created. So he's showing you something, but it's just part of a gigantic circle.
Sometimes the pattern will be at an angle, sometimes it'll be perfectly horizontal, and if you're using the 50% silvered mirror, you can also get concentric rings. When everything is working properly, the pattern is extremely sensitive to movement.
So part of what you could do is you could dissect how thick those bars are, you count the bars, do all that kind of stuff to figure out what your actually what kind of radius is you're dealing with in terms of the amount of spreading that the light's doing. And again, for them not to understand that the more I spread the light, the more path lengths I create that are long path lengths. Clearly, the entire cause of the effect is changing phase by changing path lengths.
Here I'm not even pressing on the optics table itself, but just the corner of the box, and you can see that the pattern changes.
Right, but they think this change is based on wavelength shifting. This happening, where you're changing the phase directly. And what's really happening is, no, you're changing this. You're changing where on that cone. How far the distance is on that cone by moving the cone. And that distance is less than. It's less small a difference. The amount of distance to change a whole wavelength is much larger.
Our setup doesn't allow for it, but if the main mirrors were on sliders, any movement back and forth would also change the pattern.
Again, not conceding that any movement left or right or up or down will also change the pattern.
This leads to one of the first uses of this sort of device. By measuring how quickly the fringes move, you can measure the motion of the individual mirrors down to the nanometer.
So he said again down to the nanometer, there's no real evidence they can measure that small. Light is like 500 nanometers, and you're looking for a little bit of a phase shift. So, that's a pretty big clump, 500 nanometers. And 250 would be the phase shift. You'd have to move something 250 nanometers to change its phase. So that's a lot of nanometers. So this is just such an exaggeration that we're measuring 1 nanometer of change. No, you're not. Not even close.
This property is used in some of the most sensitive experiments on Earth. One example of where this is used is in the calibration of the watt balance currently being used to redefine the kilogram.
Right, and that's sort of dangerous, isn't it? To be using a ruler that you're put the marks on it too smaller than you can see. Who knows what you're doing to your poor little meter.
In a watt balance, during calibration, you need to know exactly how quickly it moves up and down when a voltage is applied. So by mounting a mirror onto one of the arms and setting it up into an interferometer, you can measure its motion down to the nanometer. Another
Not a really good way to measure the standards, frankly.
use is in extremely sensitive seismometers. Even if I was breathing too hard while close to this, it was enough to make the pattern move.
I know, but we really don't have any evidence that can do any of the things you claim it can do. So again, like LIGO, they don't swing a lead ball over the top of the tunnel. Why not? They should be able to pick it up theoretically. So why don't they show us, gravity moving the mirror? Why don't they do that?
Alternatively, for things like LIGO, any change to the length of the beamlines will show up in the diffraction pattern.
And so again, understand LIGO, there's this very long tunnel, looks very bright, very mechanical, very nice, and they're actually shooting the light 1,600 times through it. And they're telling you that they have a mirror so perfect that the mirror always reflects the light from exactly the same location. So every photon that goes into the mirror, it leaves the mirror from exactly the same location. It doesn't go in 4 atoms one time and 6 atoms the next time and 400 atoms the next time. No, it always hits the same exact atom in the same exact position. A ludicrous expectation.
This allows you to measure the contraction and expansion of space as a gravitational wave passes through one of the beamlines.
So again, they just keep saying this is all settled science, and it was settled because some guy stood up and said we did it, and nobody really has the capacity to repeat the experiment. Nobody has the capacity to challenge the experiment because the experiment is all about computer processing and synthetics and a bunch of notions about what actually happened in the experiment, a bunch of assumptions about the fact that we can shoot photons through 1600 interactions with a mirror and be precisely certain about exactly how old that photon is, which is just plain silly.
The last use of an interferometer that I'll talk about is a special kind of spectrophotometer called a Fourier transform spectrophotometer.
Okay, I don't know if we need this. I mean, yes, there are uses for interferometers. They are good measuring tools, but they're nothing like what they claim it to be. They're claiming it can measure really, things much smaller than it really can. So we'll just leave it at that. Well, let's see if he ends with any kind of hokum pokum.
Through the double slit. Because
okay.
light can interfere with itself, we can make use of this property by building a device called an interferometer. The diffraction pattern the device produces can be used in a variety of ways to either measure the motion of mirrors, changes in beam length, or absorbance of light through a sample at a variety of wavelengths.
I don't know how to fix it.
I hope all of this has given you a better appreciation for just how easy it is to experiment with quantum mechanics.
I hate you.
And also how simple fundamental properties of the universe can be used in all sorts of more complex experiments.
Fucking window.
Now that we're more comfortable with these sorts of experiments, we'll be able to start to explore more complex phenomena.
Alright, so it's just all this hype about how it's all proven, it's all established, and frankly none of it has been. They can't take a simple experiment like a single slit and accurately analyze it, and you have to trust them about all these other complex interactions, complex experiments where they'll tell you what's happening, and you can't trust them to tell you again something as simple as throwing a rock, something as simple as the baseball analogy where they don't even use the same basic theme. They know they have a pattern of waves going in. Why don't you have a pattern of baseballs going in? Because it's the pattern. Okay, the pattern is what you're collecting on the surface. You're not collecting a baseball, just like you're not collecting a single little wave. You're collecting a pattern. So they can't even be that fair to the argument.
At some point, we'll revisit this so that we can talk about those interpretations of the double slit experiment and how some modifications to this experiment are allowing us to glimpse which of those
so they're talking like only one of these three wacky ideas. It's either Mohammed or Jesus or Buddha. That's all there is. And Buddha was a religion because frankly you can't talk to death, and Buddha claimed he talked to death, and and that death told him he should die by jumping into a fire so he doesn't have to come back again. So it is a fucking religion. But yes, that's your choice. Silly, sillier, and silliest. I mean, you really can't get much sillier than the multiverse, right? I mean, that's just so lame and such a cop-out. Oh, forget about thinking about it. We'll just say that we have a new universe every time anything happens, and then we don't have to worry about consequences or, adding it all up or any of that. We don't have to, the total doesn't have to mean anything because we're just going to say anything can equal anything.
Interpretations might be correct. And since we're familiar with the basics of optics experiments, we may even be able to experiment with things like quantum entanglement.
Oh, there we go. So, and this is all, it's not about any quantum entanglement. It's again about the fact that polarizing filters have another quirk in them. There's a certain percentage of light that is bent by the whatever you call that, the half-angled filter, the 45, the 22 degrees, filter, and the fact is that it happens progressively when you turn a filter. It breaks more light at the beginning and then breaks less at the end, so it's not something where it's proportional. It's one of those Lorentz curve liney things. And the fact that they don't acknowledge that is the only reason why they believe that any Bell inequality was violated. It's because they have an expectation for the experiment they should have never had in the first place.
So be sure to check back every other Monday for all of that. If you love quantum mechanics as much as I do, then be sure to check out my store.
If you like science, you don't have to love it, but if you like science, you like being doing smart stuff and being accurate and finding the truth, then yeah, you're not going to get it from this crap. This science ain't going to help you any. Because this is just facade science. They don't care about the principles at all. They don't want to do the work. They just want to believe in Jesus.
On Redbubble. I've already turned the Planck's constant experiment into this cool poster, and I'm already working on turning this and other videos into posters as
Oh, it's just so cool. Yeah, I'm just overwhelmed by the coolness of it all.
well. If there are other designs or items you want to see added to the store, be sure to leave your suggestions.
Science be dumb. How about that? Yeah. How many scientists does it take to analyze a single slit? Apparently bazillions.
In the comments down below. As always, thanks for tuning in to another Mad Science Monday. I've recently found out that YouTube has changed its subscription algorithm,
Oh, so I have to tell you how to subscribe and ring the bell. So I'm doing a physics video, but I have to explain, don't fart at the dinner table. Fuck. There's just no hope. It is painful, but I must endeavor to persevere. Because that's the principle here. Yeah, that's one of my principles. And nothing can happen unless you invest in something happening. So, the only way to make the investment is to endeavor to persevere. Because there's no other good reason. But anyway, so I'll just do that. And it'll work or it won't. Yeah, I know it'll work someday. I just was be kind of nice if it worked sometime in my lifetime. That would be nice. No point in giving my corpse the ticker tape parade, right? I mean, my corpse isn't going to be able to enjoy it much. But whatever. Till the next time and such, so forth and whatnot. Yeah, I've done my job. I can only reason with you. I can't make you reasonable.